Greetings. So, we will continue our discussion on angular momentum, and we will discuss today the matrix of the Clebsch-Gordan coefficients. We will discuss some further properties of the Wigner-D rotation matrix, and then we will introduce the irreducible tensor operators today. So, we know what the Clebsch-Gordan coefficients are. These are the vector coupling coefficients when you couple two angular momenta, and you can express the coupled angular momentum with these circular brackets in terms of the direct product of the uncoupled vectors, and likewise you can have the inverse transformation and represent the direct product of uncoupled vectors in terms of the coupled angular momenta. So, what we will now compose is a matrix of Clebsch-Gordan coefficients, in which we will label the rows by the direct product of the uncoupled vectors and the columns by the coupled vectors. Okay. So, there are two alternate basis sets, both are orthonormal basis sets, and you can always carry out a transformation from one to the other. So, I will illustrate this procedure by taking a specific example in which I will couple two angular momenta, both of which are equal to half. So, J1 is equal to half, J2 is equal to half, and from these we compose a third J, the J3 or the final J, which is J1 plus J2, and the size of J would go anywhere from modulus of J1 minus J2 to J1 plus J2 in steps of 1. So, in this case it can take only two values, 0 and 1, right, and for each value of J the corresponding value of M would go from minus J to plus J. So, we can already see what will be the dimensionality of this matrix, because we will begin to label the rows by M1 M2. So, the dimensionality will be 2J1 plus 1 times 2J2 plus 1. So, both are half. So, the dimensionality will be 4. We already saw in the previous slide we expected this dimensionality to be 4. So, this will be a 4 by 4 matrix, which is called as the matrix of Clebsch-Gordan coefficients. Now, this is how you compose a matrix. So, you first generate a 4 by 4 table. Do not even look at the columns first see how the labels are the rows are labeled. Okay. These are the labels for the rows. So, the first row is M1 M2, both having their highest value, which is half. So, for M1 equal to half, what is the maximum value of M2? That is half. Then what is the next value of M2 for the same value of M1? So, the next row is labeled by M1 equal to half and M2 equal to minus half. Then the third row is labeled by the next value of M1, which in this case is minus half, and for this minus half again you pick what is the highest value that M2 can take, and then go to the next value of M2 whichever it can take, and in this case it is minus half. So, this is how the rows are labeled, and the first thing to do while preparing your table for the Clebsch-Gordan coefficients is to first decide how the rows are going to be labeled. So, this is how you do that. Then you begin to label the columns and label the first column first. Label the first column such that you have the highest value that J can take, okay, and then the corresponding highest value that M can take. So, this is J equal to 1 and M equal to 1. Now, what this choice is going to give you is give you the matrix element in the first row and first column, okay, which will be equal to unity, because that is the only transformation which is possible. Now, after you label the first column, notice that I have put a question mark in the remaining 3 columns, and now we want to label these columns. We have already labeled the rows, now we want to label these 3 columns. So, after labeling the first column we will label the last one. Okay. So, we will now label the last column, and last column we will label with j equal to 1 and the lowest value, which is the maximum negative value that the corresponding m value can take, because what this will do is to give you in this position, which is the element in the last row and the last column, this value will also turn out to be 1, because that is the only combination which is possible there. Now, you already know that for the remaining elements in the first row and the last for the first column and the last column, m is not equal to m1 minus m2. So, those Clebsch-Gordan coefficients must vanish, because that is a necessary condition for the Clebsch-Gordan coefficient to be not 0. So, put 0 in all those locations. Now, you can label the remaining columns, and what you do is label them such that you get zeros over here and zeros over here as well, and you can easily do this by fixing j equal to 1 and j equal to 0, because let the value of j diminish from here and then choose the next value of 0 from this set, and now you have got zeros over here and non-zero elements along the block diagonal. So, you have okay. So, it is very easy to compose the matrix of the Clebsch-Gordan coefficient tables, and there is a simple procedure which I just illustrated. So, now we are almost ready, because we can now use the recursion relations. We derived these recursion relations in the previous class, and we have got the matrix elements in the 1 1 location and in the n n location, the last row and the last column, and also the first row and the first column. So, these two have already been pinned down, and now you can go to the neighboring coefficients using the 2 recursion relations you have. What you find on the screen are 2 relations, one corresponding to one sign, like if you take the minus sign over here, you take the upper sign over here and the corresponding upper signs in the rest of the terms. So, this is a set of 2 equations, and with these 2 recursion relations you can then generate the entire matrix of the Clebsch-Gordan coefficients. So, you really do not need to consult any book or anything, you can do it by hand. For coupling of any angular momenta in the exams you will do it by hand. So, you know how to do it. Okay. So, you will need to use the recursion relations to do that, and this table in this particular case of combining j1 equal to half with j2 equal to half, the table turns out to be 1, then you have got root 1 over root 2 in these 2 positions and 1 over root 2 and minus 1 over root 2 over here, and then the zeros elsewhere, you have got 1 over here as we already illustrated. So, let me give you one more example so that you know the method sinks in. In this case we will take one of the 2 angular momenta to be half, j2 equal to half, and j1 we will choose to be 1. So, the values of j that we can get out of it would be 1 plus half and 1 minus half. So, 3 half and 1 half, these are the only 2 possibilities. And what will be the dimensionality of the basis now? It will be 2j1 plus 1 times 2j2 plus 1. So, that will be 6. So, the Clebsch-Gordan coefficient matrix will be a 6 by 6 matrix. How will we compose it? First we will label the rows. Okay. So, we generate an area for a 6 by 6 matrix, then we label the rows, begin with the m1 m2, m1 taking the maximum value that it can and m2 taking the maximum value that it can. So, m1 can take the maximum value corresponding to j1 equal to 1, right. The maximum value for m1 for j1 equal to 1 is 1, and then m2 equal to half, then the next lower value of m2 which is minus half, then the next lower value of m1 which is 0, and then the 2 values of m2, and then you go to the lowest value that m1 can take, and then the corresponding two values of M2. So, this is how you label the rows. So, do not mix them, because if you do that you will not get the Clebsch-Gordan coefficient matrix in a block diagonal form, okay, if you do not label them appropriately. Now, you want to label the columns. So, notice that you take the highest value over here, the corresponding highest value over here, the lowest value over here, the lowest value of M, which is minus 3 by 2 corresponding to j equal to 3/2, and this is what will give you 1 and 1 in the element position number 1 1 and n, which is 6 6, 6 row and 6 column, and then you use the recursion relations to get the other values. So, you can go from one to the other using the recursion relations, okay. So, this is what it will turn out to be. So, you can generate the Clebsch-Gordan coefficient tables very easily by hand by yourself. These are cataloged on the internet. If you just Google, you will get these tables, so that you do not always have to calculate this yourself. It is a good idea to, maybe some of you might want to write a program to generate it, and these are good exercises actually. There are other properties which are very useful, the orthogonality relations of the Clebsch-Gordan coefficients, and you can already see that since you have an orthonormal basis set, so you have an orthogonality between M1 prime index and M1 and M2 prime and M2, but you can also plug in a unit operator in between, okay. Now, when you do that, this is a unit operator which is the resolution of unity in the basis, which is the basis of the coupled angular momenta. So, this is the Jm basis. So, which is why I have used the curved brackets over here, and once you plug in this resolution of unity, you have this orthogonality relation expressed as the left hand side is the same and the right hand side is a double sum of a product of these Clebsch-Gordan coefficients. You can also write this element before the other one, it does not matter, okay. So, notice that this is an orthogonality between this M1 prime index and M1, and then this M2 prime index and M2, and what is sandwiched in between is the unit operator. So, it is a very simple relationship, all that you have exploited is the resolution of unity. So, you have similar relations, you can you have to keep track of what the orthogonality is in between. In this expression, this is the other orthogonality relation that you get. This is the orthogonality between J prime and J and M prime and M, and you can get it similarly by sandwiching a unit operator, okay. So, it is exactly an identical relation, and these are complex conjugates. So, the Clebsch-Gordan coefficients being real, you can always write them with the coupled part on one side and the uncoupled part on the other, or vice versa, it does not matter. So, you will see them in different forms. We will now discuss the representation of the rotation group in angular momentum basis, and this is a very simple topic, but an extremely important one, and you will see why it is so important. You will see it being used in atomic physics and also in nuclear physics very often when you deal with angular momentum properties. So, you already know what the rotation operator is. This is the exponential form of the rotation operator. This will be expressed in a basis which is an eigenbasis of the angular momentum j, which will be a 2j plus 1 dimensional basis. So, the matrix will be a 2j1 plus 1 times 2j1 plus 1 basis, and each matrix element is the matrix element of the rotation operator in these angular momentum eigenstates, right. So, these are known as the Wigner rotation matrices. As I mentioned earlier, we have met them earlier on Sakurai's cover. So, let us have a look at this in some further detail. Now, you know that j square commutes with any one component, and since the rotation matrix for a finite rotation is also made up of a sum of these terms, okay, which generates the exponential series, the rotation matrix also commutes with j square, and therefore the rotation matrix will be diagonal in the j index. So you can always choose j as one of the indices to label it, because it is a diagonal in j index and it will be fixed for every element. So this property we will exploit, that the rotation matrix is diagonal in the j index. The matrix size will be 2j plus 1 times 2j plus 1, and you can denote the matrix element by a row index and a column index. So this is the row index m prime, this is the column index m, and the superscript j will remind you as to which angular momentum it really belongs to, okay, because so far as this superscript index j is concerned, the rotation matrix will definitely be diagonal in this index. So now let us ask, when you have a composition of two angular momenta, you take two angular momenta and combine them, generate a composite angular momentum, a sum total, an addition of these two angular momenta. Then we have seen in our previous class that j will go from this modulus j1 minus j2 to j1 plus j2, the triangle inequality that we have seen, and we will now obtain the matrix elements of the rotation operator when you are dealing with coupled angular momenta. Okay. So these are the ones that really are obviously important enough to come on Sakurai's Kaba. So the block diagonal form will contain these Wigner D matrices. The smallest block will have a dimensionality which is equal to the modulus of j1 minus j2. So it will be a square matrix. The largest one will have j1 plus j2, right, and then you will go one from the other by adding unity, okay, because j goes from the lower limit j min to j max in steps of 1. So this is the block diagonal form of the Wigner D matrix, and in each block the value of j will be different. This j is j min for this block, it is j min plus 1 for the next block, and it is j max for the last block, which is j1 plus j2. Okay. So each block will have a dimensionality 2j1 plus 2j plus 1 times 2j plus 1, but the value of j will be different, it will increase from upper left to the lower right in steps of unity, and there is no way you can reduce any one of these blocks. Okay. Notice that if you do not label your rows and columns appropriately, you can scramble this or carry out a similarity transformation on this entire matrix, okay, and scramble the elements and get a form which is not in a block diagonal form. So typically when you express it in a block diagonal form, you have what is known as irreducible representation. A reducible representation is very easy to define, it is one which is not irreducible, okay, but you know what an irreducible representation is. So that defines both irreducible as well as reducible, okay. So essentially it is important to arrange the rows and columns appropriately so that you will get the matrix in a block diagonal form. Now let us consider the irreducible representations in the composite space. The composite space will then have a number of D matrices. So this is one in the upper left, and this is D j1 plus j2 in the lower right, and you know sometimes you use the script D, sometimes a fat D to denote these matrices. So this is just a matter of notation, and different books will use different kind of symbols. So let us do a theorem that the matrix element of the rotation operator in the direct product states is the product of the matrix elements of the rotation operator in the factor states. Okay. It is a very simple theorem, but we will need to prove it. This is what we mean by matrix element of the rotation operator in the direct product state. So, this is the direct product, right. J1 M1 J2 M2 is the direct product of the two vectors J1 M1 and J2 M2, which are independently eigenvectors of two different completely disjoint angular momenta. So, there are two angular momenta J1 and J2, they have their own eigenspaces, you combine them to get a net angular momentum, and now we ask what is the relationship between the matrix element of the rotation operator in the direct product space to what it is in the factor states. Okay. So, we will prove this theorem now, and we begin this proof by first considering the response of this direct product to the rotation operator. Now, both being angular momentum states, both of these will respond to the rotation. Okay. So, J1 M1 will respond to the rotation, and the result will be expressible as a linear superposition of the component vectors in that corresponding space. So, you will carry out a sum over a dummy index M1 prime from minus J1 to plus J1, and the coefficients will of course be the Wigner-D matrix elements in the factor states, right. Likewise, this J2 M2 will also respond to the rotation, and you will get a linear superposition of an admixture of the base vectors. So, M2 prime will go from minus J2 to plus J2 in this, and you combine these base vectors with appropriate coefficients, which will be the Wigner-D matrix elements belonging to the J2 space. Okay. So, now let us write this in a slightly different form, in which all I have done is to write the Wigner-D matrix elements over here, and then I can once again get these factor states written out explicitly over here. So, it is the same expression written differently, and I compose the direct product states of these two factor states to get J1 M1 prime, J2 M2 prime, and this is the result of the operation by the rotation operator on a direct product state. So, you have to compose this superposition over double, this is the double summation over M1 prime and M2 prime. So, we get this result, and we will bring this up to the top of the next slide, which is here. And now what you do is to take its projection on another direct product state, but this time we choose this to have different indices. So, since we have already used M1 and M2 and also M1 prime and M2 prime, I have used M1 double prime and M2 double prime, so that we do not mix up the indices. So, I take the projection of this entire equation on a direct product state. So, now on the left hand side I will get the matrix element of the rotation operator in the direct product states, and here you have the matrix elements of the rotation operator in the factor states, but now you have this element as well, but you can easily recognize that this is going to give you the Kronecker deltas, because this is coming from an orthonormal basis. Okay. So, only those terms will survive for which M1 prime is equal to M1 double prime and M2 prime is equal to M2 double prime, and there is a double summation over here. So, you contract the sums, and that really completes the proof. Okay. So, this is the matrix element of the rotation operator in the direct product states, and you find that it is the product of the matrix element of the rotation operator in the factor states. So, that was the theorem that we had set out to prove, and it has a very simple proof as you have just seen. So, all you do basically is to make use of the orthonormality conditions of the basis sets and use the usual transformation properties of how an angular momentum vector response to rotation, and that is the basic relation that you already know, and you will find that almost all of this algebra is based on very simple properties of the response to the rotation operator. Now, there is another theorem which gives us a result which is known as the Clebsch-Gordan series. This is also a very important relation, so I will establish this as well, and this equation is what is called as the Clebsch-Gordan series. Notice that you have on the left hand side product of two rotation matrix elements, okay, and these are in the factor states on the left hand side, both of these, okay. This is the matrix element of the rotation operator in the J1 M1. So, this is in the eigenbasis of J1, this is in the eigenbasis of J2. So, on the left hand side you have got the matrix elements of the rotation operator in the factor states. On the right hand side you have a triple sum, then you have two Clebsch-Gordan coefficients, and you have another rotation matrix element, but this one is in the coupled state, okay. This is in the Jm basis. So, on the right hand side you have the coupled angular momentum Jm. So, this is the matrix element of the rotation operator in the coupled basis, and now you will begin to see there is a little bit of advantage in choosing a notation in which you differentiate between the coupled vectors and the uncoupled vectors. Both are angular momenta, and it really does not matter because the bracket is a bracket is a bracket, it really does not matter how you denote it, but I have chosen to denote the brackets of the uncoupled vectors by angular brackets and the brackets of the coupled vectors by these circular brackets, because it helps me keep track of what is what, okay. Otherwise they all look the same and then you lose sight of the physics in it sometimes. So, this is just a matter of convenience, and we will prove this theorem. This is what is known as what leads us to the Clebsch-Gordan series. So, we will use the previous result that the matrix element of the rotation operator in the direct product states is the product of the matrix element of the rotation operator in the factor state. So, that theorem which we just established, we will use that, and using this statement what we do is between this and this rotation operator I sandwich a unit operator over here, and I sandwich plug in a unit operator here as well, and that is all I have done in this step, which is to plug in a unit operator, but this unit operator comes from the resolution of unity in the coupled basis, okay. That is the idea. So, you plug in the resolution of unity twice, one before the operator u and one after it, and now you notice that when you look at this relationship you find in the middle the matrix element of the rotation operator in the coupled basis. Now, this is what you wanted to appear on the right hand side, okay, because on the right hand side in the Clebsch-Gordan series you wanted to see the matrix element of the rotation operator in the coupled basis, and you can discover it very easily by noticing that right here you have that element already, okay. So, it is a very simple trick, and you find this matrix element over here which is nothing but the matrix element of the rotation operator, but we also know that this is diagonal in the J index. You know that this is diagonal in the J index, so this will carry the superscript J prime with the two J's to be equal. So, J must be equal to J prime, but do not you have a summation over J prime somewhere? Here it is, okay. So, you can exploit that and use the Kronecker delta contraction. So, the sum over 4 dummy indices reduces to a sum over 3 because you exploit this delta Jj prime over here, and now you have the superscript J prime over here is J prime equal to J, and that pretty much completes the relationship that we are looking for, because You can just rewrite this as a product of these two Clebsch-Gordan coefficients, write this matrix element at the last, and you already have this result from the previous theorem that we established, right. So, we use it and we have the net expression, which is famously called as the Clebsch-Gordan series. It is a very simple proof, and all you have to do is to learn to play with these resolution of unit operators, use the orthonormalities, and you will have to do a lot of algebra using these techniques. But you run into a large number of summations, sometimes summations over 3 dummy indices, over 4 dummy indices, 6 and 7 and even 10 and more, when you do complicated atomic physics, and it is very easy to make a mistake. So, make sure that you keep track of what is what. Okay. So, you will find alternate forms in different books, because you can interchange the dummy labels. Since the Clebsch-Gordan coefficients are real, they can be transposed and you will find them written differently, okay, but they will all be completely equivalent to this, and you will have very simple ways of going from one form to another. So, what I am going to do now is to define what are known as irreducible tensor operators, and these are really important. These are in classical mechanics also we deal with physical quantities, and these are scalars, vectors and so on, right. Whatever you work with physical quantities like temperature, energy, velocity, force, momentum, these are the physical quantities that you deal with, and these are all tensors of various ranks. So, tensor of rank 0 is a scalar, tensor of rank 1 is a vector, tensor of rank 2 sometimes you call it as a dyadic, and there are various tensors of various ranks that you work with, and these physical quantities will then correspond to certain dynamical variables in classical mechanics, for which you will have corresponding quantum operators, because that is what quantization is about. So, interactions will also be represented by some operators which will be some sort of tensor operators. Okay. So, perturbations, for example, in the Hamiltonian. So, here is an energy perturbation. If you have a magnetic dipole which you put in a magnetic field, so this will be some sort of a perturbation, and you will express it as some tensor, and then you will quantize it, have the corresponding quantum form. So, all of these are made up of fundamental tensor operators, and it is for this reason that this is an extremely important topic. So, I will first define what is called as an irreducible tensor operator, ITO. An irreducible tensor operator is defined to be one of rank k, and it is actually not just a single operator, but it is a family of operators. It has got number of members. This family has got a certain number of members. The number of members is 2k plus 1, where k is the rank of this operator. Okay. So, the irreducible tensor operator of rank k is a family of 2k plus 1 operators, and you designate these by writing the rank k as a superscript and the members as subscript, and 2k plus 1 you designate by an index which goes from minus k to plus k in steps of 1. So, it has got a terminology which is very similar to what you have found in angular momentum designations, right. So, it is the same kind of notation that you carry, and the defining relationship, and this is what is called as the defining criterion. This equation is what defines this irreducible tensor operator. So, it is a family of 2k plus 1 operators such that a certain relationship holds. Now, what is that relationship? That is the defining relationship. It is this equation. It tells you how a member operator transforms under rotations. Okay. The response to rotation, and this is again something, this is not new to us, because we know how tensors are defined even in classical mechanics, right. That basically a scalar is its characteristic feature is that it remains invariant under the rotation of a coordinate system, right. Vectors are those whose components transform according to the cosine law. So, the law of transformation, how the system responds to rotations, is what defines a tensor. So, it is the same idea, it is exactly the same idea. What you must examine is how these quantities respond to rotations, and we know that the response of any operator to another operator is shown by u dagger T u, right. So, if u is a certain transformation, right, u dagger T u will tell you how it responds. So, this is what defines the response of the operator T k q to rotations, and the law of this transformation is defined by the right hand side. The right hand side tells you that the response of any member to rotation is that the result is expressible as a linear superposition of the entire family of the tensor operators with appropriate coefficients, and these coefficients are the Wigner D matrix elements. Okay. Now, you see that these Wigner D matrix elements are showing up at many new places, which is why they are really so important, and the Wigner D matrix elements appear as coefficients in this expansion. Okay. So, this is the law of transformation. This is the definition of what an irreducible tensor operator is. Now, we know what the rotation operator is. The rotation operator is 1 minus I over h cross j dot theta, okay, where this is any direction in space. This is the rotation operator. This is the adjoint. So, the left hand side is a product of these three operators. So, we have written the rotation operator explicitly now. So, it is just the definition that we have rewritten explicitly in terms of the rotation operator, and we can find what we get from the product of these three operators, and you do it term by term, because you will multiply this is a unit operator. So, you will get a term in 1 into 2 into 1, then you will get a term in 1 into t into this operator, which is the jz, okay, or ju, which is the component of j in one direction. Then you will get this term jz or ju into t into 1, okay. So, term by term you can expand the left hand side. So, let us do that. The first term is the operator t, which you get from the product of 1 into t into 1, right. Then you get these two terms, j dot theta into t, and then you get another term with a minus sign here, which is t times j dot theta, right. So, you will get the commutator, because the first one comes with a plus sign and the second one comes with a minus sign, and I have extracted the I over h cross as common, and then since you get the first term with a plus sign and the second with a minus, you get a commutator of these two, okay. And then you get a third term which will be quadratic in this small infinitesimal angle, and the square of a small angle is ignorable. So, you can throw that term, okay. You get a quadratic term which is coming from the last term. So, essentially all we have done is to rewritten the definition of the irreducible tensor operator explicitly in terms of the definition of the rotation operator and expanded the algebra. So, now after ignoring this quadratic term, you have the remaining two terms, which is the first term and the second term, which is nearly equal to the right hand side, and this nearly equal to sign only reminds me that I have ignored this quadratic term. It is of no consequence in linear superpositions. So, we will throw that term completely and we will write an equivalence hereafter, okay. So, now we have this relationship, and here these coefficients, I exploit the fact that this is a unitary operator, so I can do the transposition and complex conjugation. Okay. So, I have written this in terms of matrix element of the adjoint of the operator, and the adjoint operator you know is 1 plus I over h cross j dot theta. So, now you have a very simple relationship, and right hand side also now you can simplify, because here you have got the unit operator. So, when you take the projection of these k q and k q prime, you will get a delta q q prime, and summing over q prime you can contract the Kronecker delta. So, you should always be looking for these orthonormalities wherever you can find them, because that will simplify the algebra. So, now you have the left hand side written just as it is, the right hand side has this unit operator, the matrix element of the unit operator in k q prime and k q, which is the first summation over q prime. The second term is again a summation over q prime, but a summation of matrix elements of j dot theta. Theta is just a multiplier which I have written outside this bracket. Basically you are getting the matrix element of this j dot theta, which is a projection of the angular momentum in some direction, does not matter what. So, now you have a contraction showing up from this first term, because this is the matrix element of the unit operator. So, you get the delta q prime q. I choose the axis of quantization to be Ez just for simplicity, it does not matter whatever it is, and then you have the matrix element of j dot theta, which is the matrix element of Jz over here. So, this is the matrix element of Jz, and Jz operating on kq will give you q times h cross times the same vector, right, and that q times h cross comes out as a multiplying factor. You get the orthonormality between kq prime and kq, and then you sum over q prime, so that only the term in q prime equal to q survives, and there is only one term surviving over here. And now you see that you have got this operator which is equal to this operator, so these two terms cancel. In the remaining term you have got theta, which is just a tiny angle which is this common angle in both sides of the equation, so that cancels, and you get a commutation relation between the irreducible tensor operator and angular momentum state. We have got this essentially from the fundamental criterion of how we define the irreducible tensor operator. So, there is nothing new that we added, all we did was to manipulate the terms. In other words, this relationship can actually be used to define an irreducible tensor operator, and you can certainly define the irreducible tensor operator using this. So, these are equivalent definitions. You can define it also with respect to the j plus and j minus by working out similar algebra. I will not work out all those details now, it is a very similar exercise as we just did. Okay. And you will find in various books an irreducible tensor operator defined either by the relation at the top or by the relationship that you see at the bottom, which is in terms of how the components, the members of the irreducible tensor operator, how the family, each member of the family commutes with the angular momentum operators jx, jy and jz. Okay. So, j plus and j minus you know are made up of jx and jy. So, the commutation relations of the irreducible tensor operators can also be used to define irreducible tensor operators, and that you can take an example over here of an irreducible tensor operator of rank 1. You expect it to be a vector operator. So, you write the spherical components of this, the Cartesian components are ax, ay, az, and the irreducible tensor operators are minus 1, 0 and 1. Okay, this is an irreducible tensor operator of rank 1. So, its members will go from minus 1 to plus 1 in steps of 1, and these are the transformations between Cartesian and the spherical components, and we will be using this. In the next class we will be introducing a very important theorem in spectroscopy, which is known as the Wigner-Reichardt theorem. So now we have the tools to discuss the Wigner-Reichardt theorem. It needs the angular momentum algebra, which we have. It needs a good handle on how angular momenta are coupled. So we have that. We know how to use the rotation matrix elements. We have the Clebsch-Gordan series with us. We have got the addition theorem of the spherical harmonics with us. So now we have all the tools to establish what is an extremely important theorem in quantum mechanics, and especially in spectroscopy, and atomic spectroscopy, molecular spectroscopy, nuclear spectroscopy, in any branch of spectroscopy. Any branch of spectroscopy, it could be nuclear magnetic resonance spectroscopy if you like, okay, in any branch of spectroscopy, because what you do in spectroscopy is to look at transitions, and these transitions are from a certain initial state to a certain final state induced by a certain physical interaction, and this physical interaction is represented by an irreducible tensor operator. So what you are looking at is the matrix element of a tensor operator, okay, and the states will have some angular momentum elements. So you will have to extract the matrix element of these tensor operators in angular momentum states. What the Wigner-Reichardt theorem does is to help you look at this in a very simple fashion. So this is at the very heart of any branch of spectroscopy, atomic spectroscopy, molecular, and Zeeman spectroscopy, Stark effect, Zeeman effect, NMR spectroscopy, double resonance spectroscopy, Mossbauer spectroscopy, whatever you are referring to, okay, and that is what a physicist does, because ultimately you are going to look at interactions and transitions between a certain initial state to a certain final state. Those are the observables of a quantum system, okay. So we will introduce the Wigner-Reichardt theorem in the next class.